Good morning to all the respected dignitaries, esteemed speakers, faculty members, researchers, and participants for joining us online. On behalf of the Department of Computer Application and the Human Resource Development Center, HRDC, Integral University, Lucknow, I, Ghasia Yasmin, warmly welcome you all to the inaugural session of the 2 weeks blended faculty development program on transformative learning through interdisciplinary AI and ML applications in emerging domains. We are truly delighted to have your gracious presence with us this morning. Before we proceed further, I would like to begin with a thought. The only way to discover the limits of the possible is to go beyond them into the impossible through innovation. This thought perfectly aligns with the vision of today's FDP, where we aim to explore new frontiers of artificial intelligence and machine learning across interdisciplinary and emerging domains. This faculty development program has been carefully designed to address the rapidly evolving role of AI and ML in academia, research, and real-world applications. Over the course of this program, participants will gain exposure to emerging AI and ML methodologies, understanding interdisciplinary applications across domains, interact with eminent academicians and experts, enhancing teaching, research, and innovation capabilities. This FGP serves not just as a learning platform, but as a collaborative journey toward academic excellence and future-ready education. We are honored to acknowledge the guidance and support of our university leaders, Professor Syed Wasim Akhtar, Honorable Founder, Chancellor, Integral University, Dr. Syed Nadeem Akhtar, Honorable Pro-Chancellor, Mr. Syed Muhammad Fawzan Akhtar, Honorable Additional Pro-Chancellor, IIMSR, Mr. Syed Adnan Akhtar, Honorable Additional Pro-Chancellor, IPSR, Dr. Nida Fatima, Honorable Additional Pro-Chancellor, ISF, CIED, Professor Javed Masarrat, Honorable Vice-Chancellor, Professor Muhammad Haris Siddiqui, Registrar of Integral University. We are equally grateful to our co-patrons, Professor Syed Akil Ahmad, Director, HRDC, Professor Sunil Kumar, Dean, Engineering of Faculty, Engineering and IT. Their continuous encouragement makes academic initiatives like this FDP possible. To formally commence today's session, it is my proud privilege to invite our respected head of the department and convener of this FDP, Professor Mohammad Faisal Sir, to deliver the welcome address. His academic leadership and commitment to excellence have played a pivotal role in strengthening the computer application department. Under his guidance, the department has consistently promoted innovation, research, and quality teaching. This faculty development program reflects the visionary approach of Professor Faisal Sir, whose dedication to interdisciplinary learning and academic growth continues to inspire both faculty members and students alike. Sir, the virtual platform is yours.
Thank you, Ghasia. Respected Chief Patron, Honorable Patrons, Honorable Vice Chancellor, respected Registrar, Director, HRDC, Dean, Faculty of Engineering, esteemed resource persons, distinguished faculty members, and dear participants. A very good morning to everyone. And a special mention to Dr. Sarosh Patil, who has joined us from US. Very good morning, sir.
Good morning. Thank you for the invite.
So I, Professor Mohammad Faisal, Head Department of Computer Application, feel honored and delighted to welcome you all to this 2-week faculty development program on transformative learning through interdisciplinary AI and ML applications in emerging domains, organized by Department of Computer Application under the aegis of HRDC Integral University, Lucknow. At the outset, I would like to express my sincere gratitude to our founder and chancellor, Professor Syed Wasim Akhtar Saab, for his leadership and continuous encouragement towards academic excellence and innovation. I also acknowledge with deep appreciation the guidance and support of our Pro-Chancellor, Additional Pro-Chancellors, Honorable Vice-Chancellor, Registrar, Director HRDC, and the entire University Administration for their constant support in organizing this program. The Department of Computer Application was established in year 2003 and has steadily evolved into a dynamic center of teaching, learning, and research. Over the years, the department has focused on academic quality, industry relevance, and research orientation. We have continuously upgraded our curriculum to align with emerging technologies such as AI, machine learning, data science, cloud computing, and cybersecurity, ensuring that our faculty and students remain future ready. Our faculty members are actively involved in research publication, funded projects, FDPs, workshop, and academic collaborations at national and international level. The department regularly organizes academic events such as conferences, FDPs, expert lectures, and hands-on training programs to promote continuous professional development. Our students have also performed commendably in terms of placement, internship, higher studies, and participation in technical and research-based activities. In today's rapidly changing academic and technical environment, AI and ML have emerged as powerful interdisciplinary tools, influencing almost every domain of knowledge. Keeping this in perspective, the FDP has been thoughtfully designed to promote transformative learning, enabling faculty members to integrate interdisciplinary AI and ML application into teaching, research, and innovation. Over the next 2 weeks, participants will engage with distinguished experts through lectures, discussions, and hands-on sessions. I'm confident that this program will help participants ensure they are enhancing their pedagogical practices, strengthen research capabilities, and explore new interdisciplinary collaboration. Once again, I extend a warm welcome to all faculty members, research scholars, and industry professionals who have joined us from within and outside the university. Your active participation will certainly enrich the academic deliberations and contribute to the success of this FDP. Before I conclude, I would like to place on record my sincere appreciation for the efforts of the organizing committee, coordinators, and supporting staff for their dedication and hard work in making this program a success. Once again, I warmly welcome you to wish you all the best for this FDP. I hope these 2 weeks will be intellectually stimulating, professionally rewarding, and academically enriching for everyone. Thank you and my best wishes.
Thank you very much, sir, for your insightful welcome and for setting a strong academic direction for this faculty development program. On behalf of the Department of Computer Application, I extend a heartfelt welcome to Dr. Sarosh Patil. We are grateful to him for graciously accepting our invitation and sharing his valuable time and expertise with us. We look forward to gaining deep insights from his vast academic and research experience. Dr. Sarosh Patel received his BE degree honors in electrical engineering from Osmania University, India, his MS degree in electrical engineering and technology management, and his PhD degree in computer science from the University of Bridgeport, Connecticut, USA. He is currently serving as an associate professor in the Department of Computer Science and Engineering at the University of Bridgeport, USA. His research interests include robotics and artificial intelligence, computer vision, and biomedical imaging, and his contributions have significantly enriched both academic research and practical applications in these domains. Without further delay, I respectfully invite Professor Sarosh Patel to kindly deliver his lecture on small object detection for medical applications to share his valuable insight with us. Sir, the virtual platform is yours. Kindly proceed.
Thank you. Thank you for that very warm invite. First of all, let me thank all the organizing committee. I think it's a very commendable job. Thank you for inviting me for your opening lecture. It's my pleasure and also my honor. I think I have good friends at your university, including Dr. Asif and now Dr. Faizan Mahmood, who has invited me. So it's my pleasure to speak to you today. And as you might probably know, right now it is 12 midnight at my place. So I'll try to stay as awake as I can as I'm addressing this lecture. But let me give you a brief idea about I hope you can see my screen, right? Are you guys able to view my screen?
Yes, we can.
Okay, thank you. Thank you. I just wanted to confirm. So let me quickly give you an idea about where I am from so you have a background, and then we'll get started with the main topic, right? So I'm from the University of Bridgeport. Okay. We are a graduate school on the east coast of the US. We're very close in the northeast of the United States, very close to New York, an hour from New York, actually, and at a very short distance from Boston, which is the financial and scientific hub in the Northeast. Okay, so we are a full university in terms of our undergraduate and graduate population. We have courses and programs all the way from our bachelor's, master's, to our graduate and PhD level, right? So we are a fully accredited university. We offer programs all the way up to a PhD program in computer science and engineering. And with the AI trend, we are the first university in the state of Connecticut in the US to offer a master's in AI and now a PhD in artificial intelligence. Okay, so we have a very diverse student population, as you know, a lot of Indian students and many students from all across the world. Okay, and because we are in this richest county in the US, we are home to many of the Fortune 500 companies, and many of our students are employed there. They do internships and so on. So it's a very exciting area to be in. And also in these times when, AI, machine learning, and all of these interesting techniques are evolving, there is a huge demand for not just our students, but also for a lot of our professors who do consulting. So anyways, as I was saying, all our programs are accredited from whether it's the School of Engineering, it's School of Business, or any other health sciences. And just to give you an idea, we offer all the standard electrical, mechanical, computer science, computer engineering. But at the graduate level, we are very diverse. As you know, biomedical engineering, which I am a chair of, intersects with core engineering principles, but also with medical applications. And that is what I'm going to base my presentation today, which is, I think, very well suited for your topic because your presentation addresses AI in an interdisciplinary area. And I think I cannot think of, even though my area is also robotics and computer vision, I cannot think of a better application area for AI than biomedical engineering because, other than bringing efficiency and cost benefits, AI should really try to solve lifestyle problems or medical problems. I think that would be a really enriching technology if it solves human problems, cures diseases, and so on, right? Other than just bringing efficiency and cost benefits. So, anyways, let me get to the topic that I want to discuss with you today, which will be the lecture on a small object detection when it comes to AI, right? So when we look at the application areas of AI, one of the interesting areas right now is object detection, right? I mean, AI has solved, there are algorithms and techniques for pretty much a lot of uh, problem sets. Okay. And one of the interesting problem sets, if you look at it, is object detection, right? Whether it's object detection, segmentation, whether it is instance segmentation or panoptic segmentation. Okay. These are problems that are solved. Okay. I mean, you get pretty good accuracy if you take any uh, model, let's say YOLO, Detect, or any other SSD model, or the segment anything model from Meta, and so on, right? These problems are solved for large objects because large objects, if you look at this picture, such as a car or a traffic light or a human, they have certain features okay, that can be easily identified. And if you have enough training data, and if you have the compute and a large data set, you can obviously train them to a certain high degree of accuracy. Okay, so this problem is fairly solved. There is not much of a challenge other than making it faster or trying to segment many multiple instances and so on. What still remains a problem in this area is small object detection. Okay, so what is small object detection? Small object detection is when you have objects that are less than 32 by 32 pixels, right? So anything that is less than 32 by 32 pixel is technically defined to be a small object. And the object need not be really small, but sometimes you can be taking a picture from a very far off distance, and then the scale of things becomes very small, right? So if you look at something from a very close range, then you see it a little in its original size. But as you move away from it, or if you take a picture from a very far off distance, then you see the number of pixels shrink because as you move far away from the object, it becomes smaller in your view, right? So this is a standard classification, which is from the standard COCO data set where, you can, one of the very commonly used benchmarks, which is the MS COCO, right? And you have three categories of objects, which is anything that is greater than 96 by 96 would be a large object. Okay, and there are other very large objects also, but this is a fair enough scale for today for us to look at it. Okay. Now, to complicate things a little further, right? I mean, this is once people started using detect or YOLO or single shot detection, right? SSD for detecting objects. The next thing was to find objects in a very minute scale. So this is one of the applications here is taking pictures from satellite imagery, right? So in this case, you can see that this is a satellite image, okay, where you have all of these, whatever it might be, boats or, a port, cars, anything that is taken from a very high altitude. So they appear to be very small. Okay? And at this scale, we are trying to do two things. First, we are trying to identify the object. Okay. And then we are also trying to classify the object. So as you can see with the legend at the bottom, you can see that this is a small vehicle or a large vehicle or a ship, a container or whatever it is, right? So even though the pixel data is very small, the data is contained in very few number of pixels, whatever it might be, right? It could be 32 by 32, 20 by 20, or 10 by 20, however it is. And that amount of information sometimes is very hard to play with and decide what type of an object it is. And for the classifier to learn the class difference between these two sets, right? As opposed to saying, is this a large vehicle or a small vehicle? Okay, is this a ship or a container? Is this a storage tank or a swimming pool? Okay, so these challenges still exist. I mean, if you look at it from a close view and it's no longer a small object, you can, if you're taking it, if you're taking a picture from, let's say, a lesser altitude, things will become more and more clear and it becomes easy for us to detect and also to classify. So when we do small object detection, we are trying to solve two problems here. First thing is to identify the object, which is to draw a bounding box around it, which is a regression problem. And the other one is a classification problem. Once you identify an object, you try to fit it into one of these possible classes, right? So this is in the general public domain interest. So how is it relevant in the medical area? So let me take you a step further and we'll make the problem slightly more difficult by introducing a medical application, right? So this is a tissue that has been removed from a human, okay, uh, that is cancerous. Okay, so once a tissue is removed, what happens is this is a cancerous part of the tissue. It goes straight from the operating room to the pathology lab where they x-ray it. And what they're trying to find out is there should be enough margin around the specimen. Okay, this is known as a specimen, and there should be enough safety margin around the specimen. Okay, so these white dots that you see, okay, these are known as calcifications. This is a marker which identifies where the cancerous part is, and this is known as a clip. Okay, this is also a calcification, but these are generally benign calcifications. They are not problematic. Okay, these small ones, okay, they are generally the part that you try to remove the cancer. And what the surgeon wants to know is there is a healthy margin around this, because if there is not a healthy margin around it, the suspicion is some part of the cancer is still in the body and they need to take away more tissue. Okay, so what we try to do here is, if you look at the scale of things in this, okay, I obviously have, this is not a full resolution image because I had to fit it into a PowerPoint. But in any case, in this image, okay, things are very complicated, right? We don't have so many pixels to decide, okay? And also, this is not a color image. So this is not a 3-channel image. It's a single channel image. The only thing that we can play with here is the bit depth. So it's not a 16, sorry, it's not an 8-bit depth image. Okay, so the maximum pixel intensity does not go from 0 to 256. It goes from 0 to 65535, which is UN16, right? So it's a 16-bit depth image. Okay, that is the only thing we can really play with here in terms of distinguishing the calcifications, okay, and we try to identify these, right? And then once we know where it is, then we can decide if there is a healthy margin between these calcifications and the boundary, so that we know that the patient will not have a relapse, or there is no small amount of cancer that is left behind, or malignant tissue that is left behind in the person. Okay, so there are two things that we can work with, as I told you, right? One is the fact that this is a UN16 image. There is a greater depth to each channel, or the single channel, because it's a grayscale image, and some amount of texture, okay, because just looking at that white data will not tell us a lot of details about it. Okay, so that makes it a very hard problem to solve. Okay. And this is another example of a breast tissue that was excised from a patient. Okay, and these are annotations that were made by radiologists. Okay, these are professional doctors who make the diagnosis. And you can see that this is too close to the border, right? So they probably want to take away, sorry, more tissue from the patient because this is too close to the border, right? So these points, and if you magnify them, you'll see a small dot there, something like this. Okay, in this, it's not so very clear, but if I wish I had a better magnification here, I could have shown you here. There are small dots if you can observe carefully. Okay, so our job, okay, with our industry collaborators was that, we would develop this entire pipeline where, once you have this X-ray taken of this tissue that was removed from the patient, the radiologist would not have to spend a lot of time. The AI would pick up these calcifications, and it would be like a second opinion, right? Just so that, the radiologist doesn't miss anything in a rush, because until the radiologist okays the excision or the tissue, the patient is not stitched up. The patient is still on the operating table. They are just waiting for the radiologist to say, okay, you have removed everything. Now the patient is safe. You can stitch him back again, right? So we want to make this as fast as possible. And at the same time, we want to make sure that, we are fairly accurate in doing so. Okay. All right. So as we were consulting on this project with this company, the first thing was for us to hire a few radiologists so that we could annotate all of these, get their professional opinion on each of the images so that we can have a ground truth basis. Okay, this would serve as a ground truth for our training models. Okay, and then the next step would be to identify an appropriate model that can play with, or that can work easily with the size of images that we are talking about. These are extremely large size because we need a high resolution image to look at these features in detail, and therefore to use a model that is not only lightweight, because you don't want to run out of memory as you're training it, And at the same time, you want it to be computationally efficient, right? So anyways, so if you look at the problem set that we have, and if you plot all the annotation boxes, so we are doing a multi-class detection here, okay? So these are the red ones are the calcifications, which indicate cancerous part of the tissue. These are known as markers, which will mark how much needs to be excised from the tissue, and then the blue ones are known as clips. Okay, and they have different purposes medically, generally to mark how much depth the tissue has to be removed from, and so on. But our job is not so much to identify clips and markers as much as it is to identify the small calcifications, especially around the boundaries. Okay. So when we plot this, you will see that there is a high concentration of bounding box dimensions at less than 0 or close to 0, because this is a small object detection problem. If it was a large object detection problem, you would see them somewhere here. All these dots would be concentrated here, right? Because they happen to be a small object detection problem, this is less than 20, right? So they are all less than 32 by 32. The maximum concentration happens to be here. Okay, if it was somewhere here, our problem would be much easier. So when you overlay all the bounding boxes and center them, this is what it looks like. Okay, so the maximum 80 to 90% of our dimensions for the bounding box are so small, they are this small, right? And we have to be careful that we don't select a model that is, mostly trained on 3-channel RGB data, but it's also scalable to a single channel image like we have here, a single channel grayscale image, because these are all X-ray images. Okay. All right. So we tried a lot of models, but today I'm going to talk to you about a very interesting model, which is a faster RCNN model for object detection. Okay, so a faster RCNN model is a very interesting model because it has 2 or 3 things that are very interesting, and put together, it forms a very nice pipeline to detect, and also at the same time to classify different objects. Okay, so if you look at it, there are 3 or 4 main components. First is the convolution layers. We generally call them as the backbone of the model. Okay, and the backbone, basically what it does is it serves as a feature extraction model, right? So it's a feature extraction pipeline. Okay, so you feed in the image. As you train it, hopefully it learns how to extract the relevant features, and you get that feature map at the end of the convolution model. Okay, from there, we propose a few regions. That means we randomly throw up a area and we say, does it contain the object or not? And then we'll compare it with the ground truth and say, yes, it does contain an object or it does not contain an object, right? So that is the reason proposal network. And as you train the model, the proposal network learns which patches to propose because they have a high probability of containing an object. Okay, and then you have the once you come across the object, then you have the pooling layers and the ROI layers, which will do the bounding box regression and the classification, right? Which is standard classification that you would do when you have a multi-class problem, right? You send it through softmax and so on. Okay, and then you can do the cross entropy loss and so on. But this is the main idea that I want to discuss with you, which is discussing these 3 layers. So hopefully you have a good idea about how to work with small object detection. It also works perfectly fine if the objects are large. Actually, it works even better. Okay. All right. So this convolution layer, you can pick it to be anything that you are comfortable with. I'm going to talk about ResNet. Okay, it can be a dark net, it can be inception net, it can be exception net, it can be ResNext, or any convolution layer that you can think of. You can use it as a backbone, right? So generally, if you look at a convolutional backbone, this is how it functions, right? At each layer, you're increasing the channel depth, but you're reducing the dimensions, right? So every layer will have a stride of 2. So you go on compressing the dimensions, but at the same time, you're increasing the number of channels so that you don't lose, or you're increasing the number of features here in each of the layers so that, that information gets converted to one of the feature dimensions, okay? And that would be the backbone. So that is the first component of our architecture. Okay, as I said, there is no restriction in terms of which backbone you want to use. Okay, if you prefer a different backbone, in this case, it is using a ResNext, but you can use a ResNet. A darknet is very popular for small object detection. Okay, and then the other addition here is a FPN. The FPN is a feature pyramid network. Okay, it's a very useful addition because without it, what happens is this is what happens without it, right? So you send in an image, it gets compressed, and the data gets converted into these features. Okay, and you can use these features to detect the object. But the problem with that is you're detecting that all at a 7 by 7 scale, in which case it really does not help us. Because if you think that your object at this point, okay, let's say is 20 by 20 pixels. So here it will become 10 by 10, then it will become 5 by 5, okay? There is no 2.5 by 2.5, let's say it's 2 by 2, and by the time it gets here, it's 1 pixel by 1 pixel. Okay, at 1 pixel by 1 pixel, you really cannot tell anything. That's not enough information for us to understand anything at that scale. Okay, so for small object detection, it's really important for us to have a feature pyramid network. So what happens here is you're not detecting the object once it gets converted or when it gets shrunk to, let's say, 1 pixel. You can detect them at all layers. You can detect them at this layer, at this scale, then at this scale, and you can detect them at this scale and so on, right? So large objects can pass through all the way here and their features will get compressed and they still have enough pixels to be detected at a lower, um, at a very high stride here, okay? But for small objects like the one that we are trying here, they have to be detected in either layer 1 or layer 2, because after that, the number of pixels that form that object will get shrunk to just 1 or 2. Okay, so for example, if at this scale, the object size is, let's say, 10 by 10 or 20 by 20, here it'll become 10 by 10, divide by 2 at each layer. Okay, so if you go down the layers and you only take the last layer here, at this point, there is barely any information available on that object. Okay, so all the detection for small objects generally happens at the lower layers. Okay, so for example, in my problem here, probably this will pass through layer 3 and you can still detect this at layer 3. But these objects like this, they won't make it to the layer 5, okay, like here. They won't get all the way up here because, you're constantly dividing by 2, and by then there's nothing left of that object at such a high scale, okay? So these are high resolution layers, and as you go up, these are high feature layers. In this case, there's not much resolution, but that resolution gets converted to features because the feature depth here is very high. Here, the feature depth is very low. Okay, so that is how FPN really helps us because it collects features from all different layers. Okay, and then we can either choose to combine them or we can use them independently to do two problems, right? Which is solving the classification problem, which is telling which class it belongs to once you find a object. And the second thing is to draw a box around it, which is a regression problem, right? So you come up with a bounding box that is learned from your annotated data set. Okay. All right, so this is the ResNet, right? And just understand, I mean, this is a very popular architecture. I guess all of you are already familiar with it. The only reason ResNet works better is because of the skip connections, because generally what happens is if you use ResNet 50 or ResNet 101, the number of convolution layers are so many that you have a problem that is noticed in a lot of long models, which is the gradients vanish. We call it as the vanishing gradient problem, where you're constantly, when you backpropagate the gradient, as you differentiate this, it keeps on getting closer and closer to zero. Okay, so the skip connections really help in terms of reinforcing that and making sure that the gradients don't become zero. Okay, and that's why ResNet is very popular like this. So these are the skip connections, right? So you take the data here, you skip it and you add it here. Again, you skip it and you add it here, and so on. At the end, you get a nice feature vector. But at this point, this feature vector is pretty much, in our case, not that useful. Okay, because we want the features over here in the first and the second convolutional models, because by the time they get here, the object don't exist anymore. Okay, so it's very difficult to do small object detection on these features as opposed to getting these from here. So our FPN will really help us tap into these layers, right? So it'll tap into C4, it can tap into C5, or you can tap in over here. Right. So our job is to get as much data that we can from these layers and construct a decent FPN, okay, a reasonable FPN so that we can combine the information from all the different layers. You can either add them by doing a bottom-up approach where you constantly scale, you can use a max pool to scale it down or stride it down by 2, okay? Or you can do a reverse, which is, scale up, okay, which is the 2D convolution and, a transpose convolution and come up from the lower layers to the higher layers like this, okay? So you can do, as I said, you can do an up convolution or you can do a down convolution depending upon which direction you want to move in the pyramid, right? So generally, if you want to take these low dimensionalities and convert it back, then you can also do that, right? You can do 2 up, or sometimes we do 2 down at the same time and we add them up. Okay, because we want to predict at every scale. We just don't want to predict at the least scale. This will be the only scale prediction if you only use the ResNet without the FPN. Okay, so this helps us predict at all different scales. Generally, this scale works for large objects. This scale will work for medium objects, and the lower scale will work for small objects. So this gives us a good scaling capability in terms of identifying objects of different sizes. But if you don't use an FPN, then it's very difficult. You can only pick up on medium or large objects. Okay, so these are different types of feature pyramid networks. You can simply take them directly and try to do a prediction on it. So this would be predicting on, probably this will get only the large objects because at the scale, only those exist. At this level, medium objects, and these would be somewhere around small objects. A better approach is something like this, okay, which we discussed over here, right, where we bring the data from here and then upsample it and then again add them to the previous layer. That way, this information is again superimposed. That is again superimposed here, and then we can take a top-down approach. Okay, if you are familiar with YOLO, YOLO combines both. It does top-down and bottom-up together. Okay, so there is one more directional pathway which takes these features, does a max pool, adds them, max pool, and then adds them like that. Okay, so the second component is as important for small objects. Without the FPN, it becomes very difficult to identify these small objects. Okay, so those are two important components. And then we go to the third component of the model, which is the region proposal network. Okay, the region proposal network is simply, let me give you an idea here. Okay, so sorry, the title is misleading. It should be a region, the region proposal network. What it does is it takes this feature map, okay, and it draws a bounding box that keeps on sliding, right? It's a sliding window system, okay? With this as the center, it will propose this box as a possible candidate to contain an object, okay? And we can decide for a feature layer, how many proposals do you want? Typically, the default setting is around 1,000 or Depends on the feature map you're working with. But you can set it, that's a hyperparameter we can tune to see how many proposals you want. And each of them will be at a different, with this as a center, you'll do a proposal at different aspect ratios, right? So this will be the different aspect ratios that you can use, right? So this is 2:1, 1:1 will be a square box, and 1:2. Okay, you can configure that depending upon what aspect ratio your objects generally belong in. If you really know what is the aspect ratio of the typical object you're looking for, then you can set it up accordingly. Okay. So there are two things happening here for every region that is proposed, right? First, it's trying to get a class if the object is contained, and then it's trying to do a regression to get the 4 coordinates, right? So you can see 4K because each bounding box will have 4 coordinates like this, and the 4 corners, so that gives 4K coordinates. Okay, right? So that's the basic idea of this should have been, my apologies, this should be the region proposal network. Okay, once a region is proposed and you have a object contained within it, okay, and you decide that this is going to be a regression bounding box, the problem becomes, as you're training it, uh, the problem becomes that small objects are very susceptible to IOU loss. So it's very hard. IOU loss does not work as well for small objects as for large objects. So I'll give you an example here, right? So if you look at if you assume that C is the correct annotation or the right bounding box, and if you simply shift it by 3 small squares to the left, okay, so if you go from, for example, A to B, which is 1, 2, 3, okay, the IOU is 0.71, right? That's the intersection over union, okay? But if you go from A to C here, then it is 0.523. Okay, but if you shift by the similar amount with this is, let's say this is a medium object, you can see the drop here, right? So from A to B, here it was 0.7. For the same shift here, it is 0.5. Okay, if you look from over here, A to C was 0.5, it becomes 0.3 here. Okay, the shift is just as much. Okay, because the size of the object is small, the loss drops very fast, or the IOU parameter drops very fast. So here you can see that this is already for the same shift A to B, it's 0.3, and this is 0.08. Okay, so we need something better. Okay, when you're dealing with small objects, for large objects, this is a good enough metric to train on. But for small objects, it's very difficult, especially in the case that, as you will see when I show you the results, sometimes there are two small objects very close to each other. And if they are annotated together, they might not necessarily be detected together. They might be detected as two individual objects, right? And that creates a different type of issue where, the IOU loss will be drastically different. Okay, even though both have been accurately predicted, just because they were not predicted together as opposed to being predicted independently. Okay, so one of the ways to do that is to combine close predictions, and we have what is known as the general IOU loss, which is, we take the smallest enclosing box around the small objects, and then we compute a loss based on that. If there are two non-intersecting boxes, then that's how we'll treat them. The problem with this is this type of a loss, even though it works in theory, when you try to run it on a model, it's very hard to converge. It does not converge very fast. So this creates a problem. Okay. For some cases, it might be fine, but generally, at least I have found it for our problem that it's not a suitable metric to go by. The other option is just to look at the center, the difference in the centers of these two boxes, right? So which is the distance IOU loss, right? Which is, okay, you have the original annotation here. This is the center, and this is the center of the predicted box. So instead of doing a IOU, we simply do a Euclidean distance, right? So, and then we construct uh, a loss function like this, 1 minus IOU plus rho is a hyperparameter. This is the uh, bounding box that was predicted, and the GT is the ground truth bounding box. Okay, and C square is the diagonal, the extreme diagonal of the minimal box containing both of these. Okay, so this is a good metric to go by. It converges very fast. Okay, uh, it is I think I prefer this more than the general IOU loss because it's easy to implement at the same time. It is easy to converge also. Okay, and it's really uh, simple as opposed to the next one I'll be showing you, which is a complete IOU loss. So a complete IOU loss tries to see if the original annotation has been completely enclosed by the predicted annotation, right? So in this case, which is we have the same metric, which is this was the distance IOU. If you look at the DIOU, this is the same DIOU loss. Okay. Plus we add a certain parameter. Alpha is another hyperparameter, and V is computed based on these. I've not put up the equation for V, but it's generally based on the dimensionality of this. So all we are trying to do is trying to see that, the ground truth is enclosing the prediction, or the predicted box is totally covered by the ground truth. Okay, so that, it's totally enclosed. Okay, so my preference out of these is a distance IOU loss. It's more easy to implement, and it also converges fast. The second choice would be a complete IOU. But in any case, you can try that if you're working with different types of images. A simple IOU should work for large to medium objects, but if you're doing small objects, I recommend that you use a different IOU loss. Okay. All right. Now, before I show you some of the results that I have, let me show you one problem that we face here. Okay. So, as I told you, these images, especially with medical images, right? What happens is the size of the image here, I have cut out a lot of boundary or the blank space. Most of the image background is useless, right? You don't want to waste your training time and the training resource on training in this empty space. So generally, it's good to crop the image to this whatever regular size, okay, so that the model is more focusing on the tissue as opposed to just the blank space. Okay. Also, one more important criteria is batching. Okay. For image detection, let's say you are detecting cars, you are detecting, let's say, traffic lights, or you're detecting a ball, a dog, or anything, where the features are very established or very, very generalized. Using a high batch size is very good, right? Because it generalizes easily. The loss function is very smooth. You can converge very fast. And it's generally advised that you use a very high batch size because, it gives a good generalization. The problem with medical image training is that you don't want to overgeneralize because every tissue is different, every person is different, and for example, in my case, every calcification is different. The clips and the markers might look the same because they are manufactured, right? They look in a certain way, okay? And that's easy to tell by their shape or their size. But calcifications are naturally occurring, right? So there is no fixed feature, there's no fixed dimension, and so on. So if you use a high batch size, it'll try to generalize the shape of that object. Okay, and in this case, the generalization does not help us. Okay, we wanted to learn as many unique instances of the calcification as possible and not try to generalize too much. Okay, because if it generalizes too much, then the uniqueness is lost. Okay, but generalization is good for, let's say you're detecting cars. I mean, cars have four wheels, they have a certain shape, they have a certain structure. So generalization really helps in that case. Okay. But the preferred rule of thumb when dealing with medical images is to use low batch sizes in your training so that you can look at all the, or you can at least learn the different cases, okay? And assuming you have a diverse data set that highlights all these specific cases that you come across, okay? Now, one thing that I want to emphasize here is in medical diagnosis and in medical applications, okay, the recall is more important, okay? So generally we try to achieve a recall above 85, okay, percent, and the precision above around 40 to 50%. Okay. Why? Because recall basically informs the doctor or the radiologist, at least in this case, is that this calcification exactly looks like what the model has seen previously. Okay. With precision, we are trying to see if it can propose any more calcifications, which is a second opinion. Okay. But the recall just makes sure that this is certainly uh, a calcification that it has learned. So with our model, we are very close to, actually, we are actually better than the 85% because the company that we are working with is really trying to get a FDA approval for this. And therefore, we want to make sure that it gives us a very high accuracy in terms of recall and anything above 40 to 45% in terms of precision so that we can guarantee its performance. Okay. So one thing that I think I missed when I went over that, let me quickly cover that for you guys. So when you decide to use a model, right, and we see that our objects are very small, we need to decide at what layer we want them to be predicted. Okay. So in my case, okay, I want them to be predicted around here. Okay, in this layers, these layers over here, or let me go here. Okay. So this is generally a frozen layer. We never unfreeze because, okay, let me explain one quick thing here. As you go down the pipeline, right, what are we trying to learn? The first layer just learns whether there is, we call this as just a screening layer. Okay, this layer will only learn where there is an object, there is no object. Okay, by that I don't mean a calcification or that, but just a tissue, right? Whether there is light or no light. This will learn the edges. Okay, this layer generally learns the edges. This will learn the texture of the tissue. Okay, over here you try to learn the context. Okay, and then you try to pinpoint the object or so on, right? I mean, these are a lot of layers, but each layer is trying to learn something. Okay, so these initial layers, okay, if you're using pre-trained weights, we just leave them as they are. We don't try to retrain them because retraining those layers takes a lot of data. And if you don't have tons of data and tons of compute, it's best to leave these two layers frozen and only work on the top layers. Okay. But because our object size is so small, training the top layers does not help detect the small objects. So what we do is we freeze this first layer because we don't want to touch it. Okay. And we are using pre-trained weights. Okay, but we try to fine tune everything after that. Okay, so the small objects will be detected either here. Our best hope is to detect them here or maybe here. Okay, if it's 32 by 32, it'll make it here. But if it's less than that, it'll be around here. Okay, and after that, it'll be all large objects. So one way we can set that up in our code, okay, is by using this canonical formula, right? So as you can see, with each stride, okay, the objects are getting diminished. So you'll divide the object size by 4, then by 8, then by 16 with each layer, right? This as it goes down the layers for the resonance. So we want to do the detection at layer 1. Okay, so let's say that I want to do all my detection at layer 1 because at layer 2, I'm afraid that the object will not exist anymore. Okay, so we use this simple canonical expression, okay, where we say that, okay, my object size is going to be so and so, okay, and this is the side of the square, okay. So let's say the maximum side of the square is 32. Okay, and the maximum object, the small object size that I have is also 32. So if I do 32 by 32, it'll give me 1, and log of 1 will be 0. 0 plus 0 will give me 0. So it'll be detected at canonical level 0 at layer 0. Okay, but since I'm freezing layer 0, okay, it'll detect whatever is there. I cannot expect it to learn anything because the layer is frozen. Okay, so generally you can set K0 as 1. Okay, you can choose K0 as 1, then you can move the detection to layer 1. Okay, if you want to move the detection to layer 2, then we can set this as 2, or you can change the side of this, hopefully, if your objects are larger. Okay, so that is one trick that we can use to push the detection up and down the pyramid. Okay, so depending upon which layer you want to decide, you can import this function from torch library, PyTorch, and then it should be able to give you the parameters where you can set it up easily, suggesting which layer you want the detection to happen at. Okay, and then it does the same thing which we went through. Okay, so let me give you a quick overview of the results, right? So it does a pretty decent job, but we also have a few false positives. Okay, so if you look here, this is the ground truth. Okay, in this case, we missed this clip here. But as far as calcifications go, we have nailed most of the calcifications that you see here, and few extra ones that the radiologist will have to take a look at and either try to dismiss them or confirm if they are really calcifications, right? So what we are really worried about in terms of removing the cancer is not to have anything around the boundary, because if these are there around the boundary, the suspicion is that some of that cancer is still left in the patient. You want a very safe margin. You don't want any of these boxes around the boundary here. Okay, so that is what we are trying to detect. Okay, so for example, let's look at this case, right? This is a classic example where, the annotation by the doctor was one big box, okay, but the model picks them up separately, right? You can have so many calcifications. This is what causes a problem with the IOU loss, because this one box is now so many boxes. So it's better to use a different metric than a simple IOU loss, because the simple IOU loss says that this box, when compared to this, is very small, right? The intersection is very small, okay, and so on. So there is no problem with detecting large objects like this. I mean, these are not really large, but in any case, these have fixed dimensions, they have known features, so they can be easily detected. But such things are only detected by contrast or by the texture of the tissue. Okay, so the change in texture of the tissue, change in the bed depth, and so on, does that. Okay, so that was pretty much what I wanted to share with you guys in terms of a exciting field of biomedical engineering that is being totally changed by what is happening in AI, as you all are witnessing. Okay, and for me, the biggest takeaway from AI is to be able to solve these problems. I mean, just bringing more efficiency to business processes and data analysis does not interest me or excite me as much as solving real meaningful problems. So it was my pleasure to share this with you. And if any of you are working in such areas, I'll be happy to know more about what you guys do, or see if I can be of any help. Okay. So if you have questions, I'm available. Please let me know.
Thank you very much, Dr. Sarosh Patel. Participants, any questions or queries, please, you can ask now. Dear participants, if you have any question or queries, you can ask Dr. Sarosh Patel.
Hi, Dr. Sarosh. This is on Kidwai.
Yep.
So, as you said that no two samples are similar when it comes to this. So, wouldn't that affect wouldn't that affect multiply on an extremely large data set?
Yeah, that's a good question. I think that's a very valid question. But what I'm trying to tell you is giving you a relative understanding of how hard the problem is in terms of solving. Your observation is correct in the sense that when you scale that up over a large data set, then the number of instances and every instance being different makes it a very difficult problem. But what we are trying to teach the model is exactly what the radiologists learn, right? AI just learns like we learn by practice, right? By looking at the same images again and again. And that is what a radiologist does. Somebody with 15 years of experience is able to easily tell, as opposed to somebody with 2 years of experience, only because he has seen more images and he knows that this can also be, or this shape can also be one of the calcifications, or this shape can also be a tumor, and so on. So, to your point, yes, first, the answer is yes, there will be multiple cases. But our hope with increasing the number of parameters, okay, so for example, if you think that the model is underperforming, then you can move from ResNet 50 to ResNet 101, or you can move to ResNet 152 to increase the number of parameters so that it can learn as many possible instances as it can. Okay. And I think that can only happen with a data set that covers all of those instances. Okay. And then the second problem, again, speaking to your point, is to put them all in one class. Okay, so that it understands that they all belong to a class which is calcifications and so on, right? Because they all look pretty similar as white dots, but the shape is
Mhm.
not confirmed. Okay, and what makes it even more difficult is the background is not uniform. Okay, the signal to noise ratio, as you can know from any engineering problem, in this case is pretty bad. Okay, so either you pre-process the image to enhance the contrast and so on, which is always done in medical images to highlight this, and one of the ways to do that is to give it more channel depth. That's why we medical images don't use 8-bit images, because 0 to 256 or 0 to 255 is not much contrast, as opposed to doing 0 to 65535, which is a high contrast. So one way to understand them is to go by contrast, go by texture and the intensity. But your point is valid, and that's what makes it a challenging problem to solve.
So ResNet 150 would be able to identify more common parameters than ResNet 50. That's the.
Yeah. So the idea, and again, I'm not saying that a ResNet 50 would do that. I'm just saying that if your data set has enough instances that you're not able to fit in a ResNet 50, let's say you have too much to learn and the parameters are not enough, then the wise choice is to scale up to ResNet 101 or 152.
Thank you so much.
No problem.
Any further questions by any other participant? Okay, thank you very much, Dr. Sarosh Patel, for such an enlightening, thought-provoking, and informative session. Your insights and experiences have truly added great value to this FDP, and we are grateful for your time and knowledge. To formally conclude today's inaugural session, I am now inviting Dr. Tasneem Ahmed Sir, coordinator of this FDP, to kindly deliver the vote of thanks. Dr. Tasneem Ahmed has played a key role in the effective planning and coordination of this FDP. His dedication and meticulous effort has been instrumental in ensuring the smooth execution of this academic initiative. So,
Thank you so much, Gosia, for introducing me. Uh, Thank you, Professor Sarosh, for giving a very wonderful lecture. And today we have only this lecture. I just want to tell few things to the participants that we will be sharing a detailed FDP schedule to you. Soon we are working on it, so we will share it. Meeting link will be same for the online session, so daily you can connect with the same meeting link. And your other FDP activities will be conducted through Integral Learning Initiative, that is ILI, that is a LLMS, by which we are going to conduct your assignments and quiz to assess your learning uh, through this FDP. So now I would like to thank all the team members, all the dignitaries, our university leaders, Professor, Honorable Chancellor Sir, Honorable Pro Chancellor Sir, additional Pro Chancellors, Director, HRDC, Dean Engineering, and my team members, especially Mr. Faizan Mahmood, Dr. Asif Khan, Gausia, Dr. Adnan, all they have done a very good, made very good efforts to plan this FDP and the execution of this FDP. So I extend my grateful thanks to all the team members, all the participants who joined and their patience, especially in the morning session. We had some technical glitch, so they were all available for that time. So hope you will learn a lot from this FDP. And I congratulate all the team members, and I wish that you will learn more thing from this FDP. Thank you so much. Thank you, Professor Patel. Hope in future we will be having a more interactive sessions from you, and we'll
Absolutely. Thank
collaborate
you for
with you.
inviting me. And before I leave, I just, first of all, thank you to all of you. Thank you for hearing me out. And thank you to Dr. Asif, all the organizing committee members. And thank you for the wonderful program. But more importantly, I think somebody wrote a question in the chat that I should address before I leave. Okay. So
Yes, yes,
the
yes, sure,
question
sure.
was from Sujata. I think she mentioned that how does multi-scale feature fusion help detection sensitivity? Okay, just to quickly address that, if you are detecting at the end of the ResNet, it's very low sensitivity because all the features have been compressed. Okay, but if you're getting it at all different scales, then at lower scales, some objects, especially small objects, are better detected. So it's more sensitive to use a feature prediction network. Okay, I hope that answers that. But if you have any questions, feel free, please, to write to me. Okay, my email address is that. And for all the faculty and the staff at Integral University, once again, thank you very much, and hope we'll have more interaction in the future.